recall what we have here. Okay, so we have a general element, right? Now we are rid of our by unit domain, right? We are rid of that domain. So I have an element which I think I may have distorted a little too much, but we'll see. Okay, there we go. Okay, so let's suppose that this is a node A. Okay, let me look at them all because I don't need them all. There is a node in the back here. All right, and up here we have, okay, so this is node A equals 1, 2, 3, 4, 5, this is A equals 6, 7, 8. Okay, and the situation that we have is that CAE is CA1, CA2, CA3, right, for element E, right, and likewise D. So we would have, I would say that DAE or DBE, that's a dummy index of course, but anyway, let's write it as DBE, is equal to DB1, DB2, DB3, element E, right? Essentially what I'm going to do is to observe that now in the case of the trilinear element, how many total scalar degrees of freedom do I have, right? We've actually done this calculation, right, which is that we have NNE times NSD degrees of freedom per element. Right? Okay, so if this is the case, what it tells us is that we can actually write a CE vector, which we can define as basically being C1E. Now note, C1E is a vector, it's a 3 vector. Okay, it is the set of, it's this vector for A equals 1, right, and so on. C2E to C number of nodes in the element E. Okay, likewise DE, it's just the D vector, right? It's the collection of all the degrees of freedom that are used to build or interpolate, if you want to use that term, to interpolate our trial solution, our displacement field over the element, right? Okay, so it is a collection of 3 vectors, so it's D1E, right? So, and at that node 1, we have D1 in the 1 direction, D1 in the 2 direction, D3 in the, D1 in the 3 direction, right? Those are the 3 degrees of freedom at that node, right? Okay, so we have D1E, D2E, and so on, all the way up to DNNE, element E, right? Note that CE and DE belong to our NNE times NSD. Okay, they're big vectors. In particular, if you're doing trilinears, we have a, how many degrees of freedom on a trilinear element here for elasticity? 24. Okay, so what we're seeing is that 24 degrees of freedom on trilinear elements. Okay, and this 24 is got as the product of n and e times nsd. Okay. All right. Well, what are we going to use that for? What we're going to use that for is the following, right? We are going to use that in order to write out this first integral here, and actually the second one too. Okay, the integral on the left, this is not the integral, sorry, the sum on the left and the sum on the first sum on the right. Okay, and in particular what that's going to let us do is get rid of which of the two summation symbols on the left hand side. Right, it's going to let us get rid of the sum over a and b, right? And in this case it's going to let us get rid of the sum over a. We're not going to do anything different with the third term just yet. Okay, all right. Okay, so doing all this, what we get is the following. Okay, so now the finite dimensional weak form. Really, this is already a matrix vector form of it. Right? We are already talking of a matrix vector form. It's going to be the same following. It is sum over the elements C, E, transpose. Now, because we're getting rid of the C, A, E and the D, B, E, we also can dispense with the superscripts A and B on the KE. All right, so but what that means is that we now get a larger matrix KE, right? DE equals sum over E, C, E transpose. I'm now going to call this the F internal for element E. And like I said, we are going to wait a little to get this last term taken care of. Okay, so for trilinears, right, I'm going to stick with, well, okay, let me talk about this in general. What are the dimensions of that matrix, KE? Right, it's got to accommodate the CE transpose and DE, right, in general. Right, so that is going to be NNE cross times NSD square for the general case, right? We know that we still need to account for the Dirichlet boundary conditions, and we'll come back and do that later. Okay, so this is the general case. Right? This is also, therefore, number of nodes in the element times NSD. Okay? Just to point out, our K matrix, KE matrix now, is a block, sorry, it's constructed of many 3 by 3 blocks, right? Because each of the KABs was a 3 by 3 block, right? So we have a 3 by 3 block K11, E, Another 3 by 3 block, K1, 2, E. Because if we are working with bilinear, with trilinears, we would have 8 such blocks. But let me call this K1 number of nodes in the element E. Okay, it would come down all the way until you came down. You would have NNE rows, right? And this is KE, N, N, E, 1, right? The 1 there is for the column. Until you come all the way here, you would get K, N, N, E, N, N, E, right? For a trilinear element, we would have 8 by 8 blocks, right? 8 blocks along the column direction and 8 blocks along the row direction, right? Each would be a 3 by 3, right? Each of these is 3 by 3, right? With 3 by, well, it's actually NSD by times NSD. Okay, and likewise we would have FE internal. Right, it's a 3 vector. All right, I think this is a great place to end this segment. When we come back, we will pick up from here and complete it.